Modern municipal water infrastructure is facing a systemic failure mode. It is being breached by a contaminant it was never physically designed to intercept. These are nanoplastics, synthetic polymer fragments ranging from 100 nanometers to a maximum of 1 micron. 20th century water treatment relies on a simple premise. Contaminants are solid particles that can be targeted using physical sieving and gravity. But as a plastic particle scales down past that 1 micron boundary, its physical properties shift. At this scale, the polymer stops behaving like a suspended solid. It begins interacting with the environment much like a dissolved liquid. Engineers are deploying macrophysics to combat a microscopic state of matter, resulting in a systemic breach of our filtration systems. Traditional clarifiers and sand filters rely strictly on linear fluid flow and gravity to pull mass out of suspension. To understand why this fails, we can set up a controlled comparison between a macroplastic and a nanoplastic of the exact same material density. For the larger 2 mm PVC particle, Stokes' law applies. Gravity pulls it into a predictable downward velocity. The 100 nanometer particle escapes Stokes' law. At this size, it is dominated by Brownian motion, bombarded by surrounding kinetic vectors and bouncing erratically. The mathematical consequence of this kinetic bombardment is a negligible settling rate of just 6.9 centimeters per year. This prolonged suspension time prevents capture within a flowing municipal treatment system. Because the particle remains homogeneously dispersed, it flows in tandem with fluid dynamics, avoiding the settling beds entirely. Nanoplastics bypass primary physical separation because gravity is mathematically insufficient to overcome their kinetic suspension. This bar chart displays data from the Malta tap water study, tracking nanoplastic concentrations post-filtration. This bar chart displays data from the Malta tap water study, tracking nanoplastic concentrations post-filtration. It shows an average of 240,000 particles per liter in RO-treated bottled water. A secondary factor drives these numbers higher. The RO membranes and plastic housings themselves actively shed polymer fragments under continuous high pressure. Reverse osmosis, designed to be our most advanced barrier, creates the exact high-pressure conditions that mechanically force nanoplastic infiltration. When these particles bypass municipal systems, they enter natural groundwater recharge cycles. At the nanoscale, particles possess a massive surface area-to-volume ratio. This creates the vector effect. The nanoplastic surface becomes a highly reactive adsorption site. Specific environmental contaminants readily bind to these nonpolar surfaces. This includes heavy metal ions, persistent organic pollutants, and even common pharmaceuticals. Geological soil strata normally act as a natural filter for these chemical toxins, but the soil matrix fails to trap the microscopic nanoplastic carriers. These carriers trace a continuous pathway deep into the crustal aquifers that municipalities rely on for pristine source water. Nanoplastics act as microscopic transport vehicles, smuggling heavy metals and pharmaceuticals directly into deep earth water reserves, and eventually the tap. The intuitive engineering countermeasure is to manufacture membranes with even smaller pore sizes. This line graph tracks the thermodynamic limits of fluid pressure, showing an exponential curve in energy demanded to force water through increasingly tight molecular meshes. Operating at these extreme pressures with ultra-fine pores triggers a severe biological consequence. Rapid biofouling completely obstructs the flow. The compounding variables of exponential energy cost and rapid biofouling render tighter RO membranes economically and physically unviable. Inside existing municipal control rooms, there is a secondary problem: an analytical blind spot. Standard optical sensors fail to detect particles below the geometric diffraction limit. Plant operators cannot physically see the contamination in real time. Detection technologies like nano-FTIR and surface-enhanced Raman spectroscopy do exist, but their application is currently isolated to laboratory environments. Urban water grids are caught in an engineering impasse. They are structurally incapable of treating a contaminant they can neither afford to physically trap nor optically detect. Achieving water security requires abandoning pressure-based physical sieving in favor of advanced chemical and magnetic interventions. Magnetic extraction introduces engineered magnetized nanoparticles into the water matrix. These bind with nanoplastics, pulling them from the fluid without requiring physical pressure. Biological remediation offers another pathway, using specific engineered enzymes to target and break down synthetic polymer chains at the molecular level. The core issue is the timeline. The exponential rate of environmental plastic degradation outpaces the decades-long upgrade cycles of municipal infrastructure. Because the physics of filtration cannot meet the speed of degradation, focus is shifting towards preventing these polymers from entering the cycle entirely. International policy shifts proposed for June 2026 aim to remove specific synthetic polymers from the manufacturing stage, targeting the fragmentation process at its source. Maintaining the safety of urban brands now depends on moving beyond the physical size of the pore and addressing the unique chemistry of the particle.